All right, friends, welcome back. In this video, I'd like to go ahead and cover the last section of Chapter 5 in your textbook, and that is going to discuss exponential and logarithmic models. And so we can actually use equations involving logarithms and exponentials to help us solve various word problems, and I'd just like to go ahead and demonstrate a few problems in which we're doing that here in this video. So the first application is when you do compound interest, and you may remember from a previous video that we actually have two different formulas to be able to calculate compound interest based on the number of times we're compounding in a year, right? If we're compounding a finite number of times, we're going to use that first formula, the discrete case. But if the number of times that we can compound in a year is going to approach infinity, then that's where we're going to be using that second continuous model there. And so that's what we're specifically going to be using in this problem, because they do say continuously compounded interest. And so you notice that they gave you a table here, and I've already done the work for what I'm calling the row number 1 and found all of the different quantities that you need to find. If you wanted to pause the video here and read through some of that, you absolutely can. But I'm going to go ahead and take care of the second one here, where you'll notice that they gave us the interest rate and they gave us the amount of money after 10 years. We need to go through and find the amount of time it's going to take for our initial investment to double. We also need to figure out what our initial investment actually is. Okay, so I'm actually going to go ahead and start with the initial investment here, because one of the things that they told you in the problem is that the amount of money that you end up with after 10 years is going to be $15,000. So I'm going to go ahead and plug that in for my A value here is 15,000. That's how much I end up with. I'm going to leave capital P, the beginning amount, to my principal amount to be capital P, because I'm trying to try to solve for that here in this problem. And I'm going to multiply here times Euler's number to the power of our interest rate, which if you look up above, that's 0.065, times the amount of time. Well, remember that this is the investment after 10 years. So we're going to plug in T is equal to 10. And the nice thing about having these nice calculators is that we can go actually use them to do various things in our equation, namely to type in something like this, which is something that the calculator is going to be able to do because those are all values that we know, okay? So if I go to the calculator here and I go ahead and plug in Euler's number to the power of 0.065 times 10, then it's going to give me the following result. We're going to have about 1.9155. Now, don't clear that out of the calculator. Don't do anything like that, because you'll notice that in our work, the next thing that we're going to have to do after we figure out that number is we're going to have to divide that from both sides, okay, to get P by itself. So if I were to do that here, P is going to be approximately equal to what I get when I take 15,000 and divide it by that number that I just got in the calculator. So we could type that in. We could type in 15,000. And then simply divide by the number that we just got. Now, in order to call that up in the calculator, you could press second negative button. Okay, and that puts ANS in there, and that stands for the previous answer. So if you press enter now, it's going to take 15,000 divided by the answer that came right above it, and we get this answer right here. So $7,830.69 is going to be the amount of money that we initially invested in this situation. So that's one of the things that they asked us to find, so I'll box that. And then the only other thing that we need to find is the amount of time it's going to take this dollar amount to double. Okay, so let's figure out what double that amount would be. So going back to the calculator, I'm just going to simply pick up with the times 2, and then double that amount of money is going to be $15,661.37. I just need to figure out how much time it's going to take the $7,000 amount to double into that $15,000 amount. Okay, so if I start over here with my model for compound interest, I can go ahead and plug in the double amount. So that's going to be your $15,661 and I believe 37 cents. And that is going to be equal to your $7,830.69. That is equal to Euler's number to the power of your interest rate times time, which we're trying to find. So we're going to leave that general, call that T. Okay, now our first step to solve this exponential equation is going to be to divide both sides by the number that's sitting in front of the exponential, namely the $7,830.69. But we don't even need to reach for a calculator for this, because we already know that the way we got that 15,000 number is by taking this 7,000 number and multiplying it by 2. So we know if we divide those, it's just simply going to be 2. And then on the right-hand side, that's just going to leave you with the exponential, e to the power of 0.065 times t. And now that we have this written down as an exponential equation, we could go ahead and translate this to the language of logarithms and solve it from there. So a log with a base of e is going to be your natural log of 2 is equal to your exponent 0.065 t. And in order to figure out your time, we're just going to need to divide by the interest rate on both sides here, so 0.065 divided on both sides. And then t is going to be approximately equal to whatever we get in the calculator after typing this in. So let's clear all that out. The natural log of 2 divided by 0.065, and we end up getting as our final result 10.7 if we round to the nearest tenth. So 10.7 years is how much time it's going to take for your initial investment, your $7,830.69 to double. So there we go. Okay, so a couple of problems here where we're using our compound interest formulas to find something other than the amount of money that we're going to end up with. Sometimes you're going to be asked to find a different quantity. You notice that I've done a lot of the examples in the video for the sake of time because, again, these all are in the same general spirit of trying to find various things. So in this example, we're doing the exact same thing that we just did, finding the principal amount. So you can go ahead and pause the video and read through those works if you like. The next example, same thing. We're being asked to determine the amount of time necessary for $1,000 to double. So this is going to be very similar as the one that we just did. Again, you go ahead and pause the screen there and read through the work if you're interested in figuring out what the rest of that one looks like. That's something that you are more than welcome to do. Number 4 here, this is going to be an example of one where I give you an initial bacteria population, and you're going to use an exponential model along with some of the other information in the problem to determine the amount of time it's going to take for the population to double. Okay, so this would be an example of one where you're going to have to go through and find one of your unknown quantities first before you're able to have enough information to actually solve the rest of the problem. Okay, and so as a demonstration of that, let's go ahead and take a look at the next example, which we'll actually go ahead and do together here. So example 5, the population P of Lincoln, Nebraska in thousands is going to be represented by that exponential model right there. P is equal to 224 times Euler's number to the power of K times T, where it says here that T being equal to 0 represents the year 2000 in this problem. Okay, so let me go ahead and copy that model down here just so we can go ahead and work with it later. So there we go. Okay, so it says in the year 1980, the population was 172,000. What we need to do is we need to figure out what K is first, and then use this result to predict what the population in the year 2020 is going to be. Okay, now think with me here for a second, right? Because if T being equal to 0 corresponds to 2000, if we go 20 years prior to that, then T is actually going to be represented by negative 20. Okay, and so if we were to go ahead and do that, we need to go ahead and go through and actually figure out what that growth factor is. What is K? Okay. Well, they told us here that in 1980 the population was 172,000. So what the other thing I want you to notice here as well is that P, the population, is given in thousands. So if we were to go ahead and plug in a number for T, we're only going to be plugging in how many thousands there were for P. And so that's going to be 172 here. So 172 in place of P, and that's going to be equal to your 224 times E to the power of K times your time. And again, because we're in 1980, where T being equal to 0 represents the year 2000, if we go 20 years prior to that, then that's going to be on the number line, negative 20. And so now we just have the general setup here. We just need to go through and, of course, solve for our final quantity here. Okay, so again, this is just like solving an exponential equation because that's what it is. We're just going to divide both sides by 224 first. That's going to give you about 0.7678 and some change. Okay, which is a value that you can keep in your calculator here. I just have my notes written next to me so I know what that value is going to be equal to. I'm going to simplify that exponent to just negative 20k just for purposes of making this simple a little bit later on. And then now we can go ahead and convert this to a logarithmic equation by starting off with the log base e of that decimal number is equal to the exponent that I've got here. And so I'm just going to go ahead and write that out here. So the natural log of 0.7678 ... is equal to negative 20k. And then, of course, to go ahead and get k by itself, we would need to divide both sides by negative 20 there. Okay, and so we can get our k value pretty easily that way. And if you type that in the calculator correctly, you should be getting this k value right here. So 0.0132 ... Okay. Now, to be clear, that's not the answer to the question. They did ask us to find k, so I guess that's part of our solution, but we're going to need to use that k along with our model to use this result to predict the population in 2020, okay? So if 1980 was t is equal to negative 20, t being equal to 0 represents the year 2000, then that means that the year 2020 is going to be t is equal to positive 20, okay? And so if we go ahead and start over here with our model, that was, of course, your population is equal to 224 times Euler's number to the power of our k number, which again we calculated to be 0.0132 ... We're going to need to go ahead and take that times our time, which in 2020 would be the year, well, it'd be t is equal to 20. There we go. And all we're going to need to do is type that mess into the calculator and see exactly what that's going to be approximately equal to. And if you do that correctly, you are going to get 291.7209 and then a bunch of decimal numbers here. So in order for us to kind of interpret this, what we need to remember is that n was represented in thousands. And so what that's going to mean for us is that the population in Lincoln, Nebraska was going to be 291,721, if we were to round, is what the population is going to be in the year 2020. Okay, so being able to calculate your answer, but also being able to interpret your answer is pretty darn important for any word problem. okay? And so let's go ahead and take care of the last example here in this video, which is going to be example 6 here. It says, on a college campus of 5,000 students, one student returns from spring break with a highly contagious flu virus, which, you know, is kind of on the nose here considering the times we're living in, but we're going to persevere through the problem. It says the spread of the virus is modeled by this exponential equation right here. It says where y is the total number of students infected after t days. The college will cancel classes when 40% or more of the students are infected. So, part A here, it says how many students are infected after 5 days, okay? Well, that's a pretty straightforward application of what this model is because, again, t is going to represent the number of days after those y students were affected. So all we're going to need to do for part A is just simply plug in t is equal to 5. And so I'm just going to go ahead and demonstrate that here really quickly. So for part A, we're just going to do our model, which is going to be that 5,000 divided by 1 plus 4,999 times Euler's number to the power of negative 0.8, but then times time. And of course, our time here is going to be after 5 days. So in place of t, we're just going to go ahead and plug in a 5 and just use the calculator to figure out the rest there. So y is going to be equal to all that mess typed in at once in the calculator. You're going to get about 54.019 ... which of course means that if we interpret that in the context of the problem, that's going to be about 54 students. Okay, so 54 students we would expect to become infected after 5 days. Come on now. I just want to get to my, oh goodness. OneNote's acting up. There we go. We'll just box it in that color. Perfect. Okay. And then for part B, do this over here. It says, after how many days will the college cancel classes? Okay. So the first thing that we need for that is to make sure to read that it did say that they're going to cancel classes when 40% of the student population is going to be infected. So the first thing that we should be able to calculate is taking that initial population of 5,000 and then multiplying that times 40% to figure out what 40% of 5,000 is. And of course, that's going to end up equaling, if you do that in the calculator, 2,000 students. Okay. And so what that's going to mean is that whenever we reach for our model, we're going to need to plug that in for y. So let's go ahead and do that. So 2,000 students is equal to the 5,000 students that we started with, but then divided by 1 plus the 4,999 times e to the power of negative 0.8 times t. Again, we're leaving t general because it asks us about time in this problem. So that means we're going to be able to solve for t here, and we're going to get our final answer. Now, one of the kind of weird things about this equation is that t is actually in the denominator of a fraction. And so one of the things that we could do is we could reciprocate both sides. We can go ahead and just simply raise both sides of this equation to the power of -1. And remember that an exponent of -1 is going to reciprocate, going to give us on the left-hand side 1 over 2,000. And it's basically going to swap the bottom and the top of our fraction on the right-hand side. So we're going to say that. We're going to say 1 plus 4,999 times Euler's number to the power of negative 0.0, or 0.8 rather, times time, and that's all over 5,000 there. Okay, and now because t is in the numerator, it's going to be more easily solved for here. We could just simply go through and multiply everything by 5,000 to get that 5,000 out of the denominator in the right-hand side, which means that, of course, on the left-hand side, we're simply going to be taking 5,000 divided by 2,000, and that's going to give us about 2.5. And that's going to be equal to 1 plus 4,999 times Euler's number to the power of 0.8t. Okay, and the rest of the steps here are going to be pretty straightforward. We're basically just going to be doing our inverse operations to isolate that exponential, which I'm not going to go ahead and demonstrate here. You would basically be subtracting 1 from both sides and then dividing on both sides by 4,999. And what you would end up with here at this point would be the following. You would end up having here, after you were to convert the formula here, you would end up having the natural log of 1.5 divided by 4,999, and that's going to be equal to your negative 0.8t. Okay, in which case you could just simply divide on both sides by that negative 0.8, and you would get your final result after typing that whole thing into the calculator. Okay, so really relying on the calculator to get our responses here. What we're going to find is it's going to be about 10 days. Okay, so again, being able to get your answer and then being able to interpret that within the context of the problem, very, very important for a word problem. So I know that we kind of blazed through a lot of these examples here, but again, it's just simple, straightforward applications of the models that we have and then using our skills for solving exponential and logarithmic equations to help us get some results here. So I hope this video has been helpful to you. Please let me know if you have any questions whatsoever. Thank you very much for your attention, and I will speak to you in the next one.